I found a problem so difficult that, according to Google, even the world's fastest supercomputers would need thousands of years to solve it. That's longer than all of recorded human history. Just one single calculation. But in 2019, Google announced something shocking. They claimed they had built a machine that completed that same task in about 200 seconds. They called it quantum supremacy. That single claim ignited one of the biggest debates in modern computing. Was this a real breakthrough, or just clever math? So what was this impossible problem? It wasn't predicting the stock market. It wasn't cracking passwords. It was something far stranger. Google challenged its quantum computer to simulate pure randomness. Imagine flipping 53 coins at the exact same time and trying to track every single possible outcome. The number of possibilities explodes so fast that classical computers just hit a wall. It's not because they're slow, but because the math becomes overwhelming. Google estimated that simulating this process on a traditional supercomputer could take thousands of years. Now here's the twist. What if you didn't have to check every possibility one by one? What if a computer could explore many possibilities at the same time? Your laptop uses bits, which are either a 1 or a 0. But a qubit, the building block of a quantum computer, behaves differently. It can exist in a combination of both states at once, a property called superposition. It's not magic, it's physics. In 2019, Google unveiled its quantum processor, Sycamore, with 53 superconducting qubits. It performed that impossible randomness task in about 200 seconds. Google argued this showed a clear computational advantage, a moment they called quantum supremacy. But there was a catch. The problem was specifically designed to be hard for classical computers. It had no direct real-world use. This wasn't a practical application. It was a proof of capability. Then came the backlash. IBM, a major rival in the field, pushed back. They argued that with better algorithms and more storage, a classical supercomputer could solve it in a matter of days, not thousands of years. Still a lot slower than 200 seconds, but not impossible. The debate wasn't really about who was right. It was about what supremacy really means in this context, and that debate is still going on today. It's important to understand that quantum computers are not replacements for your laptop. They're not just faster versions of the same machine. Think of it like a car versus a rocket. A rocket isn't a faster car. It's an entirely different category of vehicle, designed for a very specific and difficult task. In the future, quantum computers can help us simulate complex molecules to discover new medicines, design revolutionary materials, and solve massive optimization problems that are far beyond today's limits. But there's also risk. Large-scale quantum machines could one day break many of the encryption systems that protect our digital information. That's why researchers around the world are racing to build quantum-safe security before that happens. Since the Sycamore experiment, progress has continued. Error rates are improving. The machines are becoming more reliable. Quantum computing isn't finished. It's not practical for most of us yet. But it's no longer just theoretical, and that may be the real breakthrough. Thanks for watching.